Welcome to the deep dive. Today we're tackling, well, frankly, one of the big mysteries in large language models, in-context learning. ICL.
That's right.
It's that really remarkable thing where these models seem to just learn new patterns from what you type in the prompt. Right there, no formal training needed.
Precisely. It's a bit like showing a chef a few pictures of a new dish and they suddenly know how to make it without going back to school.
Exactly. No retraining.
And we're digging into a really interesting paper today from Google Research. They're trying to get under the hood of these implicit dynamics.
Right. So our mission is to figure out how these LLMs are pulling off this real-time adaptation.
That's the plan.
Okay, let's break this down. Because traditional AI learning, machine learning, that involves updating model weights, right? It's this whole optimization process during training.
Correct. Slow, deliberate training.
But with ICL, it's happening at inference time. The model seems to just reconfigure itself based on the prompt, even with examples it's never seen before. And crucially, there's no obvious weight update. That's the puzzle.
That's the core of it.
Yeah.
And this led the researchers to think, well, maybe there's an implicit update happening, something hidden.
Okay.
So the paper introduces this idea of a contextual block. Think of the standard transformer block, a core part of these models. They've generalized it.
Made it more flexible.
Exactly. And they proposed that within this block, the self-attention mechanism working with the MLP, the multi-layer perceptron, kind of the model's processing unit,
Yeah.
that combination implicitly changes the MLP's own weights.
Yeah.
Based purely on the context in the prompt.
Wow. So the context isn't just data, it's acting like a subtle instruction to adjust the model internally.
You've got it. A
Yeah.
kind of silent rewiring, as you put it earlier.
Okay.
And the paper lays out the theory for this. It shows how context translates into what they term a low-rank weight update.
Low rank meaning efficient, targeted.
Very efficient, yes. Not rewriting the whole thing, just making specific, powerful tweaks. And here's the really fascinating part. This whole process looks surprisingly like a form of implicit gradient descent.
Implicit gradient descent. Okay, that's a big idea. Gradient descent is usually for training, right?
Yeah.
Minimizing errors over time.
Exactly. That's the standard way. But here they observe something similar happening during inference. As the model processes more context from the prompt, the size of these implicit weight changes gets smaller. They converge, they settle down, just like gradient descent converging during training.
So it's like optimization, but it's happening on the fly, driven by the prompt itself.
Precisely. It suggests ICL isn't just some trick of attention mechanisms. It might be a more fundamental property of these deep neural networks, their inherent ability to adapt their structure.
That's quite profound. But this wasn't just theory, right? They actually tested this.
Oh, absolutely. They ran experiments focusing on getting the model to learn simple linear functions just from the prompt. And they found the model's predictions using ICL were identical to the predictions from a model where they manually applied the calculated implicit weight updates to the MLP.
Identical.
Identical. It's strong proof for this implicit weight transfer idea. It shows the mechanism they described mathematically actually works in practice.
Okay, that's compelling evidence.
It is. Now, it's important to add a small caveat.
Okay.
This analysis currently is worked out for just a single transformer block. And it mainly looks at the effect on the very last token, the final output.
Ah, so there's more work to do to see how it scales across the whole network, multiple layers.
Exactly. How these effects cascade and interact through a deep model is the next big question. But as a foundational insight, it's huge.
So, stepping back then, what's the big picture here? What does this mean for us, for the future of LLMs?
Well, it really deepens our understanding. ICL isn't just a neat feature. It seems to be part of the core adaptive capability of these networks. They can, in a way, rewire themselves instantly based on context.
Which might help explain why they're so surprisingly good at generalizing, at tackling new things.
That's a very strong possibility. It points to a much more dynamic and flexible kind of intelligence than we perhaps thought.
Models learning, or at least adapting significantly, without what we traditionally call training. It really makes you think.
It does.
And it leaves a big question for you, the listener. If these networks can implicitly change their own structure just from the context you give them, what limits does that really remove? How might that change how we design and interact with AI down the road?
A fundamental question indeed.
Lots to ponder there. Thanks for joining us on this deep dive.